We've been talking about force for a couple of videos now, and now we're going to talk even more about force. We know about Newton's three laws of motion, and we've discussed his first two, the first one being the law of inertia, that an object will not change its state of motion unless it's acted upon by an external force. And the second one, which is basically the one that says that the sum of all forces on an object is equal to the object's mass times its acceleration. Now we move on to Newton's third law of motion. There's the dude, there's the law. It says when one object exerts a force on a second object, the second exerts an equal and opposite force on the first. Many times you've heard this as for every action there's an equal and opposite reaction. I don't like it stated quite that way. It's true, but it can be confusing as to what is meant. We're talking about forces, and we're saying that forces always come in pairs. There is no such thing as a single force acting alone. The idea is this, and don't forget that force is a vector, that the force that object 1 exerts on object 2 is always, say it with me, always equal, but in the opposite direction of the force that object 2 exerts on object 1. Got that? That's really important because it's how so many things work, from how you walk to how rockets work. Anything that moves depends on Newton's third law. It doesn't depend on Newton. He didn't invent it. Okay, God invented it, but he did discover it. One of the forces that we talk about frequently is called a normal force. Now, normal doesn't mean it's normal as opposed to an abnormal force. That would be weird. In this case, we're talking about geometrically normal. That means perpendicular to a surface. A normal force is a reaction force, equal and opposite reaction, reacting to another force that is perpendicular, which is also called normal, to a surface. So, for example, if something's sitting on a table like this, gravity is pulling down on the mass, causing it to push into the table. We call that force of gravity its weight. But at the same time, if that's the only force acting on the blue mass, it's going to fall. There's a table there that's pushing up on it. And how much is the table pushing up with? The exact same amount of force. The table pushes up on the mass with what is called the normal force. Notice that it's perpendicular to the surface of the table. The way we know that they're equal is because the object is just sitting there. If those forces weren't equal, then there would be a non-zero net force, and the object wouldn't just be moving, it would be accelerating. But it's not. So that's how we know that the normal force is equal and opposite to the weight. Now, a lot of times people see this example and think, normal forces always point up. Not true. What if someone's hands are pushing against a wall like that? Well, then they're pushing against the wall with a force that we might call F. But unless they're pushing through the wall, and they're not, the molecules of the wall kind of compress and spring back, and they push back against the hands with a normal force that again we'll call N. Notice that it's perpendicular to the surface. Of course you do. And it's equal and opposite, so the hands don't go through the wall. So those are an example of a reaction pair of forces, the kinds that were described in Newton's third law. Now, weight, something that I mentioned previously in that first example we just had, is a term that is often confused in ordinary English with mass. They do not mean the same thing. You see, weight is the force of gravity on an object. If you weigh 120 pounds, that means Earth's gravity is exerting 120 pounds of downward force on you. And the fact that you're not sinking into the earth means that the earth, or maybe the chair you're sitting on, is exerting 120 pounds of force upward on you. That's the normal force. The way we calculate the weight, the force of gravity, sometimes we call it F sub g, is the mass of the object times the acceleration of gravity. That's from Newton's second law, meaning if there were nothing in the way, the object would in fact accelerate. If you jump out of an airplane, you begin to accelerate. That g, of course, is, as previously noted, 9.80 meters per second squared, or 32.2 feet per second squared. They are the same thing. When you're near Earth's surface, it is something else, maybe only 1/6 that big if you're on a place like the moon, and somewhat less than 9.8 if you're 100 miles above the Earth's surface. So it all depends on where you are. But since most of us are on Earth's surface, this is the number that we generally use. And that's how we can calculate the force of gravity, the weight of an object. Now, one really important method that is left out of a lot of physics courses, I know in my high school physics course we didn't really talk about these, is called the free body diagram. A free body diagram simply means that you show a single object, even if it's part of a complicated system, show a single object along with its mass, acceleration, and all forces acting directly on it. The reason we do that is because Newton's laws apply not just to systems of objects, but to every single object in the system. So we can analyze things one object at a time, and it sometimes makes things much, much easier. Let me show you what I mean. Let's suppose we have this truck, very heavy object, being pushed by these four guys. Another guy's walking along, and it's going through a parking lot. You can see that because of the stripes. If we were to draw a free body diagram, we don't draw the guys and we don't draw the wheels. We just draw the truck as a single object. And so I'm going to represent it with this greenish, maybe, color, square. And let's show the various forces on it. One of the forces would be the guys pushing. We could call that force F. Another force would be some force pushing back in the car. That's actually the force of friction. Usually for the force of friction, we use a lowercase f to distinguish it from the applied force, capital F. Are there any other forces acting? Well, as it turns out, there are. One of the forces acting is the force of gravity, the weight. We could call that mg, and if we knew the mass of the truck, we could actually calculate that. Now here's an important question. Is the truck sinking into the earth? You are right, it is not, which means this is not the only vertical force acting. Another force acting would be that one. That's the earth pushing up on the truck. What's it called? Yeah, that's right. That is the normal force. Now, typically, if we were going to work a problem, we would also maybe draw some axes to show our positive directions, calling the x and y directions. And we'd have some numbers on these, but we would need something else. And that other thing we would need to know is the mass of the truck. And if we knew that, or maybe we could find it by knowing all of the other things, and using Newton's second law, we can work out problems. So that's how you use a free body diagram. Got that? Now sometimes I will ignore, say, the weight and the normal force if for some reason they're not relevant to the problem. Okay? The weight sometimes can be used to compute the frictional force, so it might be relevant to the problem. Actually, it'd be the normal force to compute the frictional force. So it could very well be relevant to the problem. But in a situation where, say, there is no friction, then that might not be an important part of the problem if it's moving horizontally. So let's try an example. A 49.5 kilogram woman is standing on a scale in an elevator. You know, this happens all the time. Just the other day, I walked in an elevator and there was a woman standing on a scale. When the elevator begins to rise at 1.86 meters per second squared, what does the scale read? Now, you know that when you're in an elevator, when it begins to rise, you feel heavier, don't you? And if you want to try something fun, get into an elevator, and if there's no one else in it, before it starts moving, start walking around in circles so that your knees bend and that they're flexing. It's a really cool experience. Make sure you're doing it when it comes to a stop up at the top as well. You have the opposite experience, so I suggest you try it. Well, now we're only talking about vertical motion here. So let's try a diagram. We'll start with a positive direction, up, and we're going to do a free body diagram. This free body diagram is a free body diagram of the woman. I don't mean to be insulting to her, but I'm going to draw her as a rectangle. What do we know about her? She has a mass 49.5 kilograms. What else do we know about her? We know that she's accelerating upward at positive 1.86 meters per second. How do I know it's positive? Meters per second squared, by the way. Well, because it says rise and I chose up as my positive direction. And there's the amount right there. Now it looks like that's all we have, and it looks like there certainly isn't enough information to finish the problem. But there is, because there are other forces at play here. For example, the woman, because she has mass and because she's on Earth, she has weight. And that weight we'll call mg, and we can calculate it. It's going to be 49.5 times, and that's in kilograms, so we use 9.8, not 32.2. So we get a weight of 485.1 newtons. How do I know it's newtons? Because we had kilograms times meters per second squared. That's a newton. So is there another force acting on the woman? Is there anything we've left out? Well, you see, if this is the only force, she's going to be falling at 9.8 meters per second squared, which would not be happy, especially at the end. So what other force is there? The scale. The scale is pushing up on the bottoms of her feet to keep her from falling. Heck, the scale isn't just keeping her from falling. The scale is pushing up right here and is actually causing her to rise. You see, the cable on the elevator is making the elevator rise. The bottom of the elevator floor is making the scale rise, and the scale is making the woman rise. And so that is a force pointed upward that we call the normal force. And if we find the normal force, that'll be what the scale reads, because that's the force with which the scale is pushing on the woman. So it's also the force with which the woman is pushing on the scale, equal and opposite, Newton's third law. So how do we solve this problem? Well, by using Newton's second law. You remember second law says that the sum of the forces is equal to mass times acceleration. So watch this. Since up is the positive direction, we use our arrowheads. Arrowheads are really, really important. Arrowheads matter to determine whether our forces are positive or negative. On the free body diagram, we just write magnitudes. You'll notice I wrote that as 485.1, not negative. That's just a magnitude. We let the arrowhead represent the direction. That's a good idea, because if I make it negative and then with a downward arrowhead, someone might interpret that as meaning, well, it should be positive because it's a negative and a negative. Okay, so just magnitudes for the numbers on the diagram. Arrowheads give you direction. That's not true with acceleration, because acceleration doesn't have an arrowhead, so it can be positive or negative. So the sum of the forces would be the normal force is positive minus the weight is negative, and that's equal to the mass of the woman, 49.5, times her acceleration, which is positive 1.86. Take a second look at that. This says sum of the forces. It says a minus sign, but we're adding n plus negative 45.1. The arrowhead says that this is negative, equals her mass times her acceleration. That's Newton's second law. Okay, take a moment and solve that equation. Okay, you're back. I get that n is equal to 577.17. Did you get the same thing? Now, if we look at the information on the problem, we have 3 significant figures in the acceleration and 3 significant figures on the mass. So we're going to round this to 3 significant figures and write 577 newtons. Why newtons? It's a force. And that, ladies and gentlemen, is what the scale reads. Now here's the weird thing. She weighs 485 newtons, but the scale reads 577 newtons. That's why she feels heavy. She feels as if she weighs 92 approximately newtons more than her actual weight. That's why you feel heavier when the elevator accelerates up, and why you feel lighter when it accelerates down. Got that? By the way, once the elevator is in constant velocity after maybe 1 or 2 seconds, you feel like you're at your normal weight again, because although you're moving, you're no longer accelerating. And if this acceleration had been 0 right here, imagine putting a 0 right here, then the normal force would be 485.1. The scale would read her actual weight. Now I'm going to pause there. We're going to do a second example in the next video, but I don't want to make this too difficult right at the beginning here. So practice some of these problems, get out your physics textbook or something, find some problems, go online, find some problems. These are not hard once you get used to them. Good luck.